Welcome to today's Explainer. Today, we're going to explore one of the absolute most awe-inspiring, frankly almost cinematic processes on our entire planet, the birth of volcanic islands. You know, when you look at a globe, it's really easy to just think of continents and islands as these static, permanent fixtures. But the truth is, the map is completely alive. Earth is this dynamic, living system, and some of the very youngest landforms on the planet are literally being created right now, just out of our sight. Which really brings us to a wildly mysterious question, doesn't it? How does a massive, brand new piece of land just suddenly appear right in the middle of a vast ocean? I mean, it sounds like magic, but it's actually this brilliant display of the Earth's internal mechanics. To really understand how an island can literally rise from the depths, we have to look way past the breaking waves and travel miles beneath the ocean's surface to the actual engine of land creation. Okay, let's jump right into Section 1. Fire beneath the ocean. All right, so let's dive into this incredibly high-pressure, intensely hot world. Just to make sure we have a really solid mental model for this explainer, we need to quickly clarify two terms that people mix up all the time. First, we have magma. That's the extremely hot liquid rock that's sitting underneath or right within the Earth's crust. But the exact second that molten rock finds a vent and erupts above the Earth's surface, it officially becomes lava. So think of it this way. Magma is the fuel waiting underground, and lava is the material that actually builds the island up above. Now, you might be wondering what keeps all that magma trapped down there, or for that matter, what lets it out? Well, that brings us to tectonic plates. The Earth's crust isn't just one solid eggshell-like layer. Actually, scratch that. It's more like a giant shifting puzzle made up of irregularly shaped slabs that literally float on a layer of melted rock down in the mantle. Because these plates are constantly bumping around, shifting, and pulling apart from each other, they create these critical weaknesses, pathways that allow all that superheated, pressurized magma to finally escape. That takes us to Section 2, breaking the surface. So, the crucial point to remember here is that growing a mountain underwater is definitely not an overnight job. We're shifting from the violent, intense heat of the mantle to a painstakingly slow, creeping timescale. This journey generally happens in 3 exact steps. Step 1 is a submarine eruption. That's when magma first pushes through the crust. Step 2, over thousands or honestly even millions of years, that lava cools in the freezing ocean water, solidifies, and slowly piles up layer by layer into a massive underwater mountain called a seamount. And then finally, Step 3. After countless eruptions, the very peak of the seamount actually breaches the ocean's surface. At that exact moment, an island is born. And hey, if you're sitting there thinking this is just some ancient prehistoric thing, consider Hunga Tonga Hunga Hapai. This is a brand new piece of land in the nation of Tonga. A submarine volcano there started erupting in December of 2014, and by the time it stopped just a month later in January 2015, it had left behind a completely new island. This stuff isn't just history, it literally happens right before our very eyes. Moving right along to Section 3, tectonic plates and hotspots. So why do these massive ruptures happen exactly where they do? Let's kind of zoom out for a global tour. There are basically 3 distinct geological zones where underwater magma finds an escape route. First, we have constructive boundaries. That's where plates pull apart and magma naturally rises to fill in the gap. Then we have destructive boundaries, which is where one oceanic plate actually sinks or subducts below another one, generating magma in the process. And lastly, we have hotspots. These are super powerful stationary plumes of magma that punch right up through the middle of a plate. Now, what's really interesting is how this plays out in the real world. Let's compare 2 really famous locations to ground this. If we look at a constructive boundary, Iceland is the perfect example. It sits right where 2 plates are actively pulling apart, which creates this massive rift zone covered with over 100 volcanoes. But contrast that with a hotspot, like Hawaii. The Hawaiian Islands sit super far away from any plate boundary. Instead, the Pacific plate is just slowly sliding over a stationary hotspot of superheated magma. As the plate creeps along, it leaves behind this incredible, continuous chain of islands. But you know, not all islands look the same, and the reason for that is purely chemical. Magma that's really rich in iron and magnesium, called mafic magma, is super runny. It flows super easily, kind of like a river, and that slowly builds those really wide, flat shield volcanoes like you see in Hawaii. On the flip side, silicon-rich magma is incredibly sticky and highly viscous. It tends to clog up the volcanic vent, trapping all these gases until it finally erupts explosively. That creates much steeper, cone-shaped mountains. So the literal runniness of the rock totally dictates the shape of the land. All right, let's shift gears to Section 4, Evolution and Erosion. Once the whole violent creation phase subsides, a totally new phase kicks off. An island might be born from intense fire, but the moment it's above water, it starts this serene yet totally relentless battle against the elements. And this brilliantly illustrates the concept of primary succession. It's truly incredible how life takes hold on what is basically just a completely barren, sterile rock. At first, you just have the cooled volcanic rock. Then, these amazing pioneer species show up. Things like lichens, which basically need zero soil, just attach right to the rock. They pave the way for mosses, and eventually, seagrasses take root. Before you know it, a pile of lava becomes a thriving, green ecosystem. But here's the catch. While biology is busy building the island up, geology and weather are desperately trying to tear it right back down. The crashing ocean waves and the wind immediately begin eroding the new land. However, the island does have one incredibly stubborn defense mechanism: igneous rock. When all that magma or lava cools, it solidifies into this exceptionally tough, hard rock layer that absolutely refuses to be easily worn away by water, ice, or wind. The difference between rock types is night and day. You've got igneous rock born straight from magma. It's incredibly tough, rock hard, and stubbornly resists weathering. Then you have sedimentary rock, like sandstone, for example, which is super soft and just washes or wears away easily. So picture this. Over millions of years, an ancient volcano stops erupting. The softer sedimentary rock surrounding it is just going to wash away over time, but that ultra-hard igneous rock, the cooled magma that plugged the volcano's literal neck, will stick around, towering over the landscape for millennia. To put that resilience into perspective, just think about this number: 350 million. If you've ever had the chance to visit Edinburgh Castle in Scotland, you probably noticed it sits perched way up on this massive cliff known as Castle Rock. Well, that rock is actually an igneous intrusion. It is the literal neck of an extinct volcano that formed 350 million years ago. The softer land all around it eroded away over time, leaving behind this unbelievable natural fortress that actually ended up shaping human history and military strategy thousands and thousands of years later. How wild is that? Which brings us to our final stop, Section 5, Earth's ongoing creation. We've been looking deep into the past to see how ancient volcanoes shape our modern cities. But we really have to remember that this whole process is far from over. There's this fantastic quote from the National Park Service that sums it up perfectly. Volcanic processes are constantly changing the Earth. Eruptions can create new islands, build and destroy mountains, and alter landscapes. I love that because it totally captures the incredible, living nature of our planet. Right now, literally as we speak, miles beneath the ocean's surface, magma is bubbling, plates are shifting, and massive underwater mountains are silently creeping upward toward the light. So, what does this all mean for the future? I want to leave you with a provocative thought to chew on. As these massive tectonic plates continue their endless shifting and magma just keeps pooling and rising through the oceanic crust, where in the world will Earth's next brand new island appear? Are we going to see it pop up off the coast of Japan or maybe somewhere deep in the Pacific? The face of our planet is actively being redrawn today. Thank you so much for hanging out with me for this explainer, and I really hope this completely changes how you look at the world map. Keep learning and stay curious.